All right, welcome to lesson 5.08. Here we're going to interpret the parameters of exponential functions in real-world contexts and also use graphs and tables to answer some questions and make some conclusions about the situation that we're modeling. Let's go ahead and get started. All right, so here's the discovery problem. It's a fairly common situation for anyone who has taken a science class. So we have two functions here, and they model the number of bacteria in one of two dishes. So n sub 1 models the number of bacteria in dish 1, and n sub 2 models the number of bacteria in dish 2 at any time t, which is measured in hours from the start of the experiment. So here are the questions you want to answer. Go ahead and copy down the intro, and then the questions. How many bacteria are in each dish when the experiment begins? Part B, in which dish will the bacteria increase? In which dish will it decrease? And by what percentage each hour? And then part C, a third dish is given by the equation below, n sub 3 here. Rewrite it in order to determine the hourly percentage increase for the third dish. So go through, try this on your own. Go ahead and press play once you finish. We'll go through this a little bit together, and if there are parts that I help explain, you can go ahead and pause again and finish it out on your own. All right, let's start with part A here. This is pretty simple. The experiment begins when t is equal to 0. And so dish 1 is going to have 800 bacteria. Setting t equal to 0, this becomes 1. 800 times 1 is 800. And then setting t equal to 0 here, I'd have 500 times 1, which is 500 bacteria. All right, so next we're looking for which dish has bacteria that are increasing and which dish is going to be decreasing in the number of bacteria. So we can see pretty clearly here that dish 1 has a base of 0.7, which means that each time t increases by 1, we're going to multiply by 0.7 and thereby decrease the amount that we have. So dish 1 is going to give us a decrease. And I'm writing this small without full sentences only to save room here. So you should write this out in full sentences in your notebook. And in which dish will the bacteria increase? That would be dish 2, as the base there is greater than 1. And when we multiply by something greater than 1, we are going to increase the value. The question now becomes, by what percentage are we actually increasing or decreasing? Let's start with the increasing. So let's start with dish 2 here. So I'm just going to go ahead and write out the function that gives us the number of bacteria in dish 2. Now, what do we notice here? Every time we increase by 1 hour, meaning t increases by 1, I multiply by 1.21. And I know that makes the value bigger, but just how much bigger? To see that, I'm going to rewrite 1.21 as 1 plus 0.21. The reason I want to do this is that I know multiplying anything by 1 retains 100% of it. And I also can interpret multiplying by 0.21 as keeping only 21% of it. So when I rewrite it like that, it will be very easy for me to make the determination. Okay, look at this setup here. Every time t increases by 1, I will multiply by 1 plus 0.21. So think about multiplying 500 by 1 plus 0.21. 500 times 1 gives you all the 500. It keeps it the same. Then multiplying 500 by 0.21 is going to leave you with only 21% of it. And we're adding, so it's going to be 500 plus 21% of 500, which means you're increasing by 21%. And that's going to occur each time t increases by 1, so each hour. So for dish 2, we have an increase of 21% each hour. Now we want to look at dish number 1, and we know for dish number 1 that we have a decrease, but by what percentage is it decreasing? I want you to go ahead and try this one on your own using the same methodology we used for dish number 2. It really is the same thought process. Once you try it, go ahead and press play, and we'll take a look at it together. Hopefully you found this actually to be a little bit more intuitive maybe than the first dish that we looked at. Notice here that I'm multiplying by 0.7 each time t increases by 1. Well, when I multiply by 0.7, I am keeping 70%, or I'm left with 70% of what I multiplied it by. And if I am left with 70% of something, that means I lost, or the value decreased by 30%. Now notice the way I said that. I said that 70% of something is losing 30%. And just how I wrote 1.21 as 1 plus 0.21, I can write 0.7 as 1 minus 0.3. And that will really illustrate that multiplying by 0.7 loses 30% of the value that I had originally. So I'll rewrite that now. Notice when I rewrite it here, I can see very clearly that each time t increases by 1, I will multiply by 1 minus 0.3, which is just 0.7. When I multiply by 1 minus 0.3, if we just do that thought experiment, multiplying 800 by 1 would give me all of the 800. Multiplying 800 by 0.3 would give me 30% of it, and I would be subtracting, which means I'm left with, of course, 70%, but also means that I lost or decreased by 30% of the 800 that I had. So here I'm decreasing by 30% each hour. All right, let's take a look at the last one here, part C. I want you to, now that you've seen part B, go ahead and pause and try part C on your own. I think you'll be able to get it just fine. And then go ahead and press play and we'll take a look at it together. All right, so in evaluating this function here, what we'll notice is that when t changes by 1, the exponent actually changes by 2, since it's 2 times t. And that means that when t changes by 1, meaning when 1 hour goes by, we're not just multiplying by one of these base values, we're actually going to multiply by 2 of them. And so that doesn't tell me what I'm multiplying by each hour. In other words, it doesn't allow me to figure out the percentage increase each hour. So what I need to do is rewrite this expression so that I have t isolated in the exponent. I encourage you to try this on your own, and then go ahead and take a look at the exponent rule that we've actually brought up fairly recently that you're going to want to use here. So what you want to recall is that if you have two things being multiplied in an exponent, you can choose to raise the base to one of those exponents first and then to the other. So I can rewrite this as 200 times 1.21 squared to the t power. Now 1.21 squared is a value that I can find very easily using a calculator, and that will allow me to rewrite the expression with my exponent as just t, so that I can clearly see what I'd multiply by each time t increases by 1. Doing so gives me a new base of 1.46. So I have 200 times 1.46 to the t. And rewriting it as I have done previously now as 1 plus 0.46, I can clearly see that the percentage increase is going to be 46% each hour. So what we just discovered is a way to rewrite exponential growth and decay functions in a way that allows us to make a lot of meaning about the situation that we're given. So if we're dealing with an exponential growth model, we can rewrite the function in this form. Notice what I'm doing is I'm just rewriting the base as 1 plus some value, and whatever that value that I'm adding on there gives me the rate that it's growing at. And so as we saw in the discovery problem, we had 1 plus 0.21, and since multiplying by 0.21 gives me 21%, I can see that it's increasing at a rate of 21% per whatever the time period was. Similarly, with exponential decay, it'll just be 1 minus whatever that rate is, and so that allows me to look at the rate at which it's decaying. So rewriting in this way can be very, very helpful, and hopefully doing so will allow you to actually see it without rewriting it, just when we're given an exponential function. So go ahead and make sure you've written these down and that makes sense to you, and you've written any questions that you have down. A couple of other things to keep in mind is that in both cases, the a value, the leading coefficient, gives the initial value or the y-intercept of the function. We've seen this before, and that's important because in real-life situations, the initial value or the y-intercept is generally very meaningful. The last thing to discuss is that graphing these functions or making a table of values, I should put an S here, making a table of values can help us to draw conclusions about the situation. So if you find yourself needing to answer some questions about the situation, make sure that drawing a graph is something that you consider in order to make sense of it. What I'm going to do now is give you a problem to work on and conclude on your own so that you can compare with your teammates tomorrow, and then we can move on to some extra task-like problems. Let's take a look. So this problem should seem kind of similar. We've talked a lot about investment, and we're going to look at 3 investment strategies here, each of which is given in function form. So the 3 functions model the value of different investment strategies, strategy 1, 2, and 3, over T years. I want you to compare the investments over a 10-year period. So we have done this before, and I want you to sort of think back to the level of specificity you wanted to have for that 10-year period. Right? It's important for you to really think it through and provide evidence and have a visual representation for you when you're explaining. A couple of things that I want you to include are the yearly growth of each investment, what we talked about today, a graph or tabular table representation, and I want you to write out your investment advice. If you were recommending one of these investment strategies, how would you do so? Okay, so write out the advice you would give. We'll take a look at it tomorrow, so make sure you've got a well-written piece of advice.